Hello and welcome to the second lecture on BCH code. My name is Smith Kumar Chaube and today we are going to discuss parity check matrix for the BCH code. So we can define the code word of a BCH code in the following manner, that a binary n tuple v is a code word if and only if the polynomial vx, which is defined in this manner, that vx is equal to vn minus 1 x n minus 1 plus all the way up to v naught, has alpha, alpha square, alpha cube and alpha 2 to the power 2t as its root. If you recall that these are the roots of actually the generator polynomial, and since this code word vx is simply message polynomials times generator matrix, then vx should also have these as its code word, right? So since alpha is the root of vx for I is equal to 1 less than equal to 2t, then we can say that when I put alpha I in this polynomial vx, I will get 0, right? Because it's alpha is basically the root of vx here, isn't it? So this is going to be true, that vn minus 1 alpha I to the power n minus 1 all the way up to v naught is going to be equal to 0, right? This equality can be written as a matrix product, right? As vn minus 1, vn minus 2 all the way v2, v1 and v naught. In the similar manner, if I will consider I is equal to all the way 1 to 2t, I will have these as equation, right? So I will have basically 2t equations here, isn't it? So I'm going to consider parity check matrix HBCH as this: alpha to the power n minus 1, alpha to the power n minus 2 all the way up to 1, and then here I'm going to replace alpha by alpha square, alpha cube and alpha 2t, right? So this is going to be my parity check matrix for the BCH code. Now if I consider that BCH code, then transpose of that pre-multiplied with v is going to be equal to 0, right? Which is consistent with the definition that we have followed for cyclic code. Okay, so if an n tuple v satisfy the above condition, alpha I is a root of the polynomial vx. Therefore, we must be a code word in the t-error correcting BCH code. So using this parity check matrix, we can actually determine whether a particular code word is part of that BCH code or not. Okay, so HBCH is parity check matrix of the code, and if we consider conjugates of alpha I, because there are certain redundant information here in this BCH code, so we can actually remove the redundancy, right? By considering the conjugate of alpha I, if we remove all the conjugates of alpha I, then I will have alpha, alpha cube, alpha 5 all the way up to alpha 2t minus 1, and then you know that there are going to be certain other redundancies here. It's still redundant, but I'm not going to remove all the redundancy, but one can actually remove all the redundancy in this BCH code. Okay, so binary parity check matrix of the BCH code, if each entry of HBCH is replaced by its corresponding m tuple over GF2 arranged in column form, we obtain a binary parity check matrix of the code. Either we can have a HBCH in this form, or I can replace alpha, alpha cube, alpha square by their n tuple and their power, right? So using that method, one can also determine the binary form of this BCH code. Okay, now we are going to consider something called BCH bound, and BCH bound is basically for example, there is a theorem here that the t-error correcting BCH code defines the minimum distance that it should be at least 2t plus 1. It is generally greater than 2t plus 1, but it is minimum. This is the minimum value of the minimum distance, right? So the parameter 2t plus 1 is usually called the design distance of the t-error correcting code. Actual distance is generally greater than 2t plus 1. The true minimum distance of the code might be larger than 2t plus 1. So you can understand that this is the lower bound for your minimum distance, and this is what is called BCH bound. So thank you for tuning in. I will see you in the next lecture.